Welcome to the June 20th OMR Architecture Meeting. So today we have an update from Mark on JitBuilder 2 and some of the progress that he's made. So turn it over to him. Take us through it.
All right. Let's do it. Hopefully people can see that.
Yep.
All right. So I realized a little while back that I hadn't talked very much about JB2 and what I've been doing for a while here, and given that we hadn't had an architecture meeting in a while, it felt like I could fill in some content here and try to update people on where things have been going, because I have been making sort of slow, steady progress in this direction, and I still intend to do greater things with it. Unfortunately, this presentation came together very late. In fact, I was modifying slides well as I got here, so I expect some of it to be kind of confusing just because it came together so late. So I will apologize for that aspect, and I'll try to do better on that in a later talk and clarify some things, because I did happen to choose a fairly complicated topic to go through for most of it. However, I thought I would start by just kind of, I always put this slide up at the beginning of every single one of these talks, basically to remind people of what JB2 is all about. It is the sort of extension to, or the evolution of the original JitBuilder API, which now I've created quite a long time ago. But JitBuilder was interesting for a lot of use cases, and people used it for a lot of things, but it also highlighted a bunch of problems with using it, and I wanted to fix those with JB2. The dual mental model between the original API and how the OMR compiler works was identified as kind of a pain point, and the logging, debugging, analysis, not sort of working on the level at which people were using JitBuilder was a substantial inhibitor. I also wanted to make things a lot more extensible and a lot more dynamically extensible, so I didn't want to have to statically compile a whole bunch of stuff together. I wanted the freedom to be able to create different kinds of compilers in the same process, loading different kinds of things into that compiler. And so JitBuilder 2 was a way of kind of experimenting along those kinds of paths, and to do it outside of the kind of framing for how we did things in the OMR compiler. And so it's kind of evolved into a framework that allows most of the core capabilities of a compiler to now be extended quite dynamically. You can plug behavior in using shared libraries. Basically, you create a thing called an extension. It has a single object, which is actually called extension, that represents all of the content in that shared library to the rest of the compiler, and then you can load those things dynamically. And if you don't load it, you don't have to care anything about it. And if you do load it, you can use all of the facilities that are inside it. So with that sort of refresher, I thought I would also, because it's been a long time since I've presented any of this, and I'm sure it's not front of mind for basically anybody other than me. So I thought I would just go through a quick refresher on some of the JB2 IL. It's actually changed a little bit. That should be IR, actually, because I stopped using IL, because it is a representation and not a language. Anyway, but I can't seem to get the acronym out of my head. So I'm going to just spend a brief time kind of going through one example kind of IL that came out of one of the unit tests that I've written recently. And then I wanted to talk a little bit about code generation, because there's some interesting complexity there in how you do code generation in the context of JitBuilder 2, especially around the fact that it can be dynamically extended, and it's actually kind of a complicated problem to solve. And I think I've managed to do it in such a way that I didn't really end up tying things together the way that you would expect them to get tied together, perhaps. And then I have a brief little bit at the end where I want to talk about the integration of JB2 into OMR, as I still have that goal in my head to do that. But my mental model for how that could work has changed basically through the process of doing this code generation work. It clarified a few things for me, so I think there's a better model going forward. So I'm going to try and go through all of that, and I expect by the end of the code generation section, everyone will be completely confused, so I'll set you up for that right now. I did not have time to write this in a easily digestible way, and I apologize for that, but I'll get you as far as I can, and then, like I said, I will come back and try to do a better job of it later. but I didn't want to cancel this meeting at the last minute. All right, so let's start looking at the IL just to refresh people's minds for how this works. So one of the things I've been doing lately is writing lots of unit tests. So there's the one main unit test, which is it's not a unit test, it's like 225 unit tests that test the OMR code generation thing. I wanted to show you what happens when you do one of the particular unit tests that's in there, which is this add 16-bit integers. So, you know, it's kind of like adding the short values from Java or whatnot. Anyway, so when you run this test OMR unit test, I've actually changed, I made a modification inside the source code for that thing that sets a thing called trace strategy true, which will trace the strategy that's used to compile that particular unit test. And so when you do that, this Google test thing, so framework, so you get a whole bunch of output on various tests that are run, and then eventually you get down to adds in 16s, which is the one that I added that call for true, and it starts spitting out this kind of output. And I'll be going through this in bits and pieces, so you shouldn't have to kind of digest it all in one go. You'll have time. The first thing I'll point out is that the sort of the begin and end pieces of this, the test does actually pass. There's actually 12 tests that are embedded in here, and it's so inefficient that it actually compiles the method 12 times and then runs the method with different input 12 times. That's why it's 7 milliseconds. It's actually a lot faster than that. Most of the unit tests that are written are, take place in 0 to 1 milliseconds, but this one just has a lot of test cases that get compiled over and over and over again. And of course,
is the S on the name means that it's plural, or is it
it's plural.
Signed?
It's plural.
Okay.
In 16 is signed by default, but
right.
The data type is actually, it's the data, anyway.
Right, okay, I get it.
Let's not get into that level of detail. So then, all right, so I'm gonna just jettison this piece at the end here because it's kind of hanging at the bottom of the slide, but let's start looking at the output here. So because I specified this trace strategy true bit on the input when I compiled this function, it starts generating all of this output with some tags and some nice kind of ways of kind of breaking things down. At the very beginning, so like Testarossa, JB2 has the notion of strategies, kind of like cold, warm, hot, etc., which are really just sequences of passes that get applied when you do a compile. So you can say, I want to compile with this strategy, and it will go and apply the list of passes that are specified as part of that strategy. And any extension can define new strategies, new passes, and add them together. And then if you want to compile something, you just specify a strategy, which is really just a number to the rest of the compiler, and it will go off and apply that strategy. There is a default strategy that's created in JB2 called CodeGen. That's the one that's actually named here, which really just, the whole point of this strategy is just to use JB2 to convert the intermediate representation that you create into some other native executable code. So it doesn't have a notion of what is doing that executable, what's doing that code generation yet. But it does have a strategy whose purpose is just, you can think of it kind of like no-opt in Testarossa. Don't do anything, just generate code for me. But I don't know how you're going to do that yet. It contains a single pass, which is actually the next one here, called CodeGen Dispatcher. And CodeGen Dispatcher is a specific example of a thing that exists now in JB2, which is a dispatcher, you can imagine, which is really just a templated, very simple kind of pass, which goes around looking to see whether there is a code generator path that's been loaded by some extension. And in this case, since I'm running test OMR, it's actually loading a code generator, or it loads I've loaded an extension called OMR Gen, which is a code generator for going directly to the OMR compiler IR. And so in this particular example, that's the one it's going to run, but it doesn't say that here anywhere. It's just, this is what the CodeGen dispatcher thing is doing. It's going off and finding a code generator to dispatch to.
We just lost your screen a few seconds ago.
Really? Gone, like completely gone?
Black.
That's exciting.
I still see it.
You still see it?
Oh.
Yeah.
That's why you should never be in the room with me when I present. I'm kidding. Is anyone else having the same problem that Daryl's having?
I can see it too.
All right. Well, feel free to come over here and watch if you want. The right person had the problem, I guess. It's the other way of looking at it. All right. So this CodeGen dispatcher thing just finds some code generator. It doesn't really matter for this part of the example what it finds, but it finds some path that is a code generator that's going to go and generate things. Now, also, just like Testarossa, the passes that, because we're tracing here, it's going to show the IR before and after, and so that's what this before IR thing is showing you. It's the IR before the code generation pass has been performed. So you can think of this kind of like the post-opt trees that get displayed at the end of the optimizer, or the IR that's input into the code generation scheme. And then one new thing that I've added to JB2 recently, which is to essentially create a single object called an IR object, which is, it captures the entire state of the IR at a point in time. So it provides a way of interacting, I guess, with the entire state of the IR. So one interesting thing that you can do with an IR object is you can clone it, and it will go and recursively visit all of the elements of the IR, and it will create a completely separate copy of everything, so that you could snapshot the IR at a particular point in time, or well, I guess that's what clone would do, is would snapshot it in time, and then you could, I imagine one or both of them evolving separately based on how what things you do to the resulting IR objects after that. So at this point, I guess I'll just start going through this. This concept never really existed before. The IR has its own memory allocator, or it can have its own memory allocator. So it can be allocated in different memory than everything else that's put there. It could be a very local allocator, or it could be even the compiler's allocator, the compiler lifetime allocator, if you wanted it to be there. But it's not tied necessarily to a particular compilation, is one of the other interesting consequences of this. So IR can actually exist outside of a compilation. Now, let's go a little bit through. So now I'm just gonna, the rest of the output is basically going through the various pieces that are associated with the IR object. So the most important one is kind of what is this representing the IR for? And in JB2, that's a compile unit. So this one's, everything gets an ID in the compiler. So this is U86. What that means is we've probably created 85 functions up until now, and this is the 86th one that we're compiling. It's the compile unit. It is a compile unit that represents a function. Right now, JB2 can only create compile units that are functions, but that doesn't mean it couldn't create other kinds of compile units like traces or version basic blocks or whatnot. And so it's a name called add int 16s. And attached to this unit, it also has a bunch of information about where that thing came from in the code. So it has a source code location from the actual testomr.cpp file that I wrote, that's where the class is that defines what this function actually looks like, right down to the line number. So that's different than a source location, which is something you can also specify in the IR for the various pieces of the function. But this is the kind of like the creation location, the source code that's actually creating this, that resulted in this IR being created in the first place, or this unit. All right. The next piece in the IR is a thing called a type dictionary, which will be familiar to people who have used JitBuilder before. So similarly, it has its own ID, and you can have different kinds of them. You can even have parent ones. You can link them together, etc. There are, by default, if you create a type dictionary with the base extension, it goes and creates all the primitive types, the same primitive types that the JitBuilder API has. The only one that matters for this one is the 16-bit integer type, because it is the 16. We're adding two 16-bit integers. So this is the only type that gets referenced in the rest of the IR. So I've taken out everything else. And it only shows this, and it's basically just, it would show a list of types. This one is T2 because it just has the identifier 2. You can see the size in bits, the name of the type in 16 type is what it's called, and then that it's a primitive type. If you had created a struct type, it would show you a struct type and tell you what fields were in it with what offsets. If it was a field type, it would show you what the offset of that field type is and what its name is and what its what the type of the field value would be, etc. But basically, this goes through and summarizes what all these types are.
So all the primitive ones are coming from T0? Like that's the linked dictionary?
So in this case, the linked dictionary is actually a dictionary that's created by the compiler. So it's a dictionary that has the lifetime of the compiler object, not the compilation object. So this is a dictionary that has the, well, this dictionary here, this T197 guy, has it's called the compile unit type dictionary. So it gets created when the compile unit gets created.
Okay. So when you said that by default, all of the primitive ones get created?
Only when the base extension is loaded.
Okay.
So the primitive types are all defined by the base extension. So you have to load the base extension, and then these types get created in your type dictionary. All right. Then similarly, there is a symbol dictionary for holding symbols. JitBuilder, the original API, didn't have symbols, but had a very poor notion of symbols. They were strings. So now they've been JitBuilder 2 has symbols, so it's just the same exact construct as the type dictionary, except it maintains symbols. In this case, you can see there are two symbols, S1 and S2. They both have type T2, so the S1 underscore T2 mechanism notation just says an ID for the symbol and tells you exactly what type it is, so you can see the consistency of it through the IR description. It has a name, and then this is a parameter symbol, so it just means it's a local variable that's actually a parameter of the compile unit. And then there's also a literal dictionary, but in this particular test, there aren't any literals, so it doesn't really show you what they look like. If it had created a literal, it would create, I think, an LVID underscore type, and then the number, so the type of the literal, and then the details of what that type actually, of what that literal actually is. So it'd be like an int 60, it could be like an int 64 of 1 or something like that. So the literal 1. And all of the literals that would be referenced in this IR object would be present in that literal dictionary, in principle. All right, that's the end of the dictionaries. Then we get to one of the other new things in JitBuilder 2, which is the context. So context is basically describing the local variables that you have access to in this compile unit, as well as how to interact with the outside world. So in the case of a function context, for example, that includes the return type of the function and its parameters, so that you can know how this compile unit interacts with things outside of it. If this were a different kind of a compile unit, like if it were a trace, for example, there might be something like a register state that would be true on input and output, or a virtual machine state, or a CPU state, or those kinds of things. Or basic blocks could be also have a additional state associated with them. How the basic block interacts with the things that come in and go out of it. If you wanted to talk about those in detail. You can't do that right now with JitBuilder 2 because there's nothing that does it, but the fundamental capability is there. And that's abstracted by this context thing. So this is a function context. This is the root, sort of the function context for the whole function. So it doesn't have a parent context. You can't actually link them together as well. One scenario where that might work is if you were doing, or might happen, is if you're doing inlining, for example. You could imagine the inlined code having a different context than the outer code. So that can get captured via the function context. In this case, that has a return type, which is T2, which is our 16-bit integer type again, and the two parameters that we just saw in the symbol dictionary. And then the other piece that I've added recently, or not recently, but probably since I've talked to you very much about it, is in JitBuilder 2, the code is now organized into what I call scopes. Scopes are just groups of builder objects from the original JitBuilder code. So builder objects correspond to essentially the code between curly braces in a C function, for example. And then a scope, you can organize different code paths under different scopes if you wanted to. Again, the different scopes could also apply to like an inline function. You could have the blocks for a particular function having a different scope object than the outer blocks. Why would you want to do that? I don't know. Maybe they have different security contexts and you want to make sure that whenever you move between two scopes, you're doing something in particular to verify that the security status allows that to happen. I don't know. There's lots of different things that you could do with this. Right now, it's not leveraged very much in the infrastructure right now, but the goal is to enable things like that, as well as I intend to use it in the debugger at some point. So in this particular function, this add int 16s. We have one scope, which is the overall function scope. It's the scope that's associated with the function. A scope has entries. In this case, there's only one entry, which is the entry 0. Its ID is E0. It is a builder entry, and I'll show another example of a different kind of entry later, but basically the builder object that is the entry point for this scope. So if something wants to enter this scope, it enters via this entry, and it's B1. And then you can see B1 is listed here. B1 has a name. It has a bunch of things associated with it. It sort of knows about its scope as well. And then it has a set of operations that are in here. And this is a more very different than TR, more similar to how something like LLVM, I guess, lays out its operations, and then it stores things into values. The values are always annotated with their types, so you can see them very quickly that they all line up. By if you saw anything other than a T1 or T2 in here, you might look more carefully at that. But basically, there's a load operation for each of the parameters to load the left and the right value, add them together, producing a result, which then gets returned. And so there's various ways to refer to these things so that you can go searching for them very quickly in a log to find, how are these things being used or being adjusted or transformed, etc.
So this is just a linear set of operations. There's no branch.
That's correct. Correct. In this particular case, yes. In more complex cases, you can have operations that refer themselves to other builder objects, like a for loop operation. One of these operations could be a for loop, which would refer to a B2, say, and then how that that operation would then determine.
Okay, so the operations don't have to be simple operations.
Correct. Correct. They can be quite complicated, in fact. Just like the original sort of calls that you could make with JitBuilder were allowing you to assemble much more complicated kinds of things. Okay, that's basically the end of the IR. Man, I really can't get rid of that. The IR example, just to again give people a flavor for what this looks like, and the kinds of things that that are generated. This is one example of a unit test. It's like this OMR test OMR thing has 4,500 lines of hundreds of tests that get run against all of the various opcodes that I now support in the OMR code generator, as well as all the combinations of different types, etc., just to make sure that everything works. And you'll be comforted to know that I did not find any bugs in the compiler when I did that, other than the bugs that I wrote into the unit tests themselves. Nonetheless, it's still valuable to have these things. All right, so I'm going to switch gears now into sort of the exercise of trying to figure out how to do code generation in a world where you don't know what's loaded. And so this is the moment when, as I apologized at the beginning, this is the section of the talk that came together very, very, very recently and may lose you along the way. So I apologize again for that. I will come back and clarify this, but let's see how far we can get with this. So the basic challenge here with code generation is that it's naturally kind of an n by n sort of like a multiplicative complexity problem here, right? We have different extensions in JitBuilder 2 that can define lots of different types of operations and different types of types and symbols, etc. And in principle, the compiler doesn't know about any operations of an extension that hasn't been loaded, and it's supposed to know about all the operations of something that has been loaded. But that happens at runtime. And so that's one sort of degree of multiplicity. I can talk. The second one is around the fact that you could do different kinds of code generation, right? You could be trying to generate code by calling JitBuilder. You could be trying to make code by generating OMR compiler IL directly. If you wanted to, you could write code that would generate LLVM IR directly. And so you have this other degree of multiplicity that you don't know what types of code generation you might want or need. And so how do we accommodate all of these different kinds of variations that exist without kind of ending up in everybody needs to know everything about everybody else? I don't want to tie everything together. The whole point of this design or this design spectrum was to try and find ways to make a compiler that has exactly what you need and nothing and not more than you need, and give you the flexibility to be able to do things dynamically at runtime. But ideally, you still want to have some protections here, right? You don't really want you could throw, caution to the wind and do the sort of JavaScript approach to this and say, well, I'll just look to see what's there when I get there. But you'd also kind of like to have some protections in place to say, if I'm writing an OMR code generator and I claim to support an extension called base, it would be nice to actually know that I've supported everything that's in base, or at least in that version of the base extension, and not that I've left something on the table that's just going to barf when somebody finally tries to generate it. And so the solution that I've implemented here, which I guess from the setup of the complex setup of the problem, you can probably imagine that the solution is also quite complicated. But it ends up kind of hanging together quite well, I thought, at least in my head. And it basically, you need some basic mechanisms provided by JB2 itself. And then you need a little bit of static and dynamic collaboration between the extensions and code generators. And let me see how well I can do to explain some of this to you. So let's start with different code generators. So as I mentioned when I was talking about the IR at the very beginning, there's a strategy called CodeGen, which is a very simple thing. You can ask the compiler's core extension, which is always loaded for the strategy CodeGen, and then you can pass that into the compile, and as I described earlier, that will go and dispatch to whatever code generator is loaded. So what is a code generator? So from the JV2's perspective, there's a class called code generator, which you probably predicted, which can then be subclassed by extensions to create different examples of a code generator, right? So there is a JB extension, which defines a JB code generator, which is the code generator that will translate JB2 IR into calls to JitBuilder to generate code. And there is now, I've never talked about this before with people, but now there is an extension called OMR Gen, which defines a thing called an OMR code generator. It's a little bit confusing because there actually is an OMR code generator class in the OMR compiler project. But anyway, this is a code generator for translating JB2 IR directly into OMR compiler IR, so without going through the intermediate step of JitBuilder. And depending on which extension gets loaded, that type of code generation is going to be used by this CodeGen strategy by virtue of that dispatcher mechanism that I talked about earlier. And I believe I have a slide that talks a little bit more about that in a minute. This subclass of code generator is basically responsible for the main task of generating whatever kind of code is needed, right? So this dispatcher thing is going to call basically a virtual function called perform on it for the compilation, and it's going to expect a return code back that says whether it succeeded or whether or not there was an error. And if it generates success, then it's expected that it will store a native entry point for the generated start PC of the native code that got generated into the entries list. We saw that in the IR earlier. And so this is an example of this is the same entry 0, but it has two entry points, one of which is named E0, which is a builder entry. That's the builder object that corresponds to the entry point. And then as part of this code generation thing, a native entry point has been added, which has an entry PC of whatever that thing is. And so the idea is that you can call this to call the native entry point for this thing. And then other stuff happens as part of the compile process. It doesn't just leave it there sitting in a native entry, but that's the basic expectation of this code generator object. That's the kind of high-level API. And there's a lot of more detailed API that's in there, but I'm not going to go through that in very much detail. So how does this unnamed code generator dispatch thing work? So as I sort of alluded to before, it doesn't name a specific generator. It uses a thing called a dispatcher T, with T is code generators. It's just a templated class. A very, very simple one. And basically all it does is goes and says, has any extension registered a code generator object? And the expectation is that if an extension like JB extension or OMR Gen extension loads, they create their code generator object and register it with JB2 so that this dispatcher guy can find it. and it will automatically look up anything that's been registered as a code generator and call their perform function. And in principle, you could even register 2 of them and call 2 and generate code twice if you really wanted to, which would create some interesting scenarios, none of which I've actually explored yet, but seems like it could be interesting for testing, for validation, even for development purposes, to be able to kind of double check or generate code for more than one code generator at the same time. But that is in principle supported by this generic dispatching mechanism. Excuse me, throat's drying out. All right. So then there's this other multiplicity problem that I mentioned, that is that we have to kind of divide this OMR code generator or JB code generator or whatever code generator across all of the different kinds of extensions that you can load into JitBuilder 2. So how do you implement that when you don't know which extensions are going to be loaded? And the idea here at a high level is that we're going to take each one of those and split out the support for various operations and types and symbols into their own classes. And yes, that sounds awful, but it's actually not that bad when it boils down to it. Because, I mean, you're already kind of separating things out into extensions, so having this code generator piece separated out into these different bits and pieces isn't really so bad, at least in the ones that I've done so far. So you end up with an OMR code generator for the things that are defined by the core extension, an OMR code generator for the things that are implemented by the base extension, an OMR code generator specifically for things that have been defined by the func extension, etc. And so that leads us to kind of 2 problems. How does this main OMR code generator object manage the dispatch to these extension-specific objects? Again, without assuming that any of them actually exist. and then there's this kind of, this consistency problem that I mentioned before, where how do you make sure that a code generator really supports all the things that are in each one of these extensions? So let's talk about those in turn. This is where it's going to start getting confusing, because this is about where I was generating slides up until about just less than an hour ago. So code generation obviously starts in the main code generator object, right? It's that perform function that I showed before that gets invoked. And then that object goes through what did I write here? Follows a process to set up the target native function, but various IR objects are handled by the extension-specific code generator object. See, I don't even understand what I wrote on my own slide here, but let me let me try to say this. So as part of generating the code for OMR, say for a particular IR that's in front of me, I have to go and handle a bunch of things that are in the IR. I have to associate code paths with all of the builder objects. So in the case of if I was generating to OMR, I would have to create TR blocks that are associated with the entry points to builder objects and so forth. And then I would have to walk through the operations in a builder object and translate those into TR nodes and possibly new TR blocks in the generated code output for the OMR compiler. And so how do I do that? So as the main JB2, like the OMR code generator object, as that's walking through the various operations of a builder, for example, it takes advantage of the fact that every IR, every piece of the IR is tagged by the extension that created it. So if I created an add operation, for example, that add operation got created by the base extension, because add is something that the base extension has. And so from that add operation, I can get to the base extension. If I had a load operation, load is created by the func extension. And so from a load operation, it would take me to the func extension object. And then, yeah, no one's going to get this. So the generic OMR code generator's gen code, so this is asking to generate the code for this operation, this OP operation here. It basically takes the operation, asks what extension created this operation, and then it asks to see if there's an add-on for this OMR code generator extension add-on. This is something that the OMR Gen extension creates and tacks on to the extension object, and asks for its extended code generator thing, and then it calls gen code on that. So in principle, what I'll try to summarize from that is there's an object via this process. The main OMR code generator gets access to an OMR specific, like an OMR code gen specific and extension specific object for handling this operation, which is what these guys are, right? This is an OMR specific, extension specific code generation object. So these guys can be found by looking for one of these add-ons on the extension that created this operation. So I know that sounds complicated, and I'm not sure I expect everyone to have grokked it, but that's basically the idea, is that it goes from the operation to the extension tells it how to find the right code generator object. And all of these dispatch things can be set up ahead of time. They don't have to be kind of set up, they're all set up when the extensions are loaded originally, not on the fly throughout compilation or whatnot. Yeah, here's where I realized everyone would be lost. So on the previous slide, there's this thing, this code generator for extension. Yeah, this guy here, code generator for extension. It's just a base class for creating these objects. And it's a base class that establishes how the main code generator object can collaborate with those other very specific objects that I talked about before. And every extension defines a subclass for its own operations, for its types, for like a subclass that handles its operations, its symbols, its types, its etc. So the example is, in the base extension directory, code generator for base implements that gen code thing and has to handle all of the operations that are declared by the base extension. So notice this is not OMR specific. This is something that the base extension itself implements. So it's kind of like the base extension makes a bunch of stuff available, and this code generator for base thing makes sure that any code generator that tries to generate code for base actually does handle everything that's in base. Those earlier classes that I showed before then have their own subclasses of this thing, the OMR code generator for base, which basically extends that code generator for base and provides the actual OMR specific generation for the operations that are defined in base, or the types that are defined in base, or the symbols that are defined by base. And that subclassing is what helps ensure that you do all the right things, basically. And like I said, I kind of expect everybody to be lost right now, so I don't think that's anybody else's fault but mine, because I just did not have enough time to try to tease apart these concepts better to explain them to other people. So it does all make sense in my head, but that doesn't necessarily mean I've convinced anybody else that it does. I recognize that. So I apologize for not having been able to spend enough time on this ahead of this meeting to get that all in place, but I'll try to keep working on this and get better at it. This is the end of the code generation section of the talk, so risking lots of weird questions, I will pause to see if anybody wants to ask about code generation. Everyone's asleep. I don't blame you. All right, I'll move on then to the last part of it. Earlier, in the last time that I talked about this, it was probably last fall at this point, I had talked about a way of bringing JV2 into, like, JV2 was an extension of the OMR compiler, so it was an OMR compiler itself, subclass, and therefore it was kind of tied to either JitBuilder or the OMR compiler. And as part of this, exploring how this code generation thing could work, as well as trying to figure out how I could both have a code generation for through JitBuilder, and also have a code generation through the OMR compiler, and later have a code generation that would go through the OpenJ9 JIT, it sort of struck me that it didn't make sense that JB2 was an OMR compiler itself. Just because, I mean, even though all three of those things are OMR compilers, there are differences between them that make it really difficult to unify anything that runs on top of them. As I found when I tried to get JitBuilder running inside of the OpenJ9 JIT at one point. There are some very fundamental pieces of the compiler that are just different and remain different between OMR and OpenJ9 that make it really hard to get that working. So, I've retreated to a different model here where I haven't done this code refactoring yet, but I'm through the exercise of doing the code generation for JitBuilder and for OMR, I'm convinced that it will work. It's just a matter of trying to figure out how the pieces learn about each other. So the new proposal is for JB2 to basically become its own top-level component. So it will no longer be an OMR compiler extension, and that means it won't actually be able to generate, at least in its current form, it won't be able to generate any native code itself without the help of some other component in OMR. That doesn't mean we couldn't write a code generator in JB2. In fact, it would be great to do that, but there isn't anything like that right now in JB2. So it would essentially isolate itself as a compiler IL that can't do much itself. And then some of the things that I've currently implemented in the JB2 directory, I'm going to move into either the compiler directory or the JitBuilder directory, so that you can, so that there would be a way to load the JB extension with the JIT to work in conjunction with the JitBuilder compiler, without necessarily having to always have a JitBuilder compiler. I guess the other advantage of this is you could actually build JB2 without having any compiler in it, so it'll be a lot smaller because it's only 37,000 lines of code, and it won't necessarily need the OMR compiler or JitBuilder plus the OMR compiler, and it could target other compilers as well. Overall, I think this seems like a much more rational approach and a much easier way to imagine integrating JB2 into the OMR project. And like I say, I think this whole approach extends relatively well if I can get this working for the compiler and the JitBuilder directories in OMR. I don't expect to have very much difficulty in trying to figure out how to make it also work in the context of OpenJ9, which was always been a long-standing goal of mine, and I think it would enable, again, some much more interesting things to happen. So it's kind of like my last summary page, which I wrote in the 3 minutes before I walked over here. As I've said, I think at the end of every one of these presentations, I've made lots of progress since the last presentation, and there's still lots to do. And I'm definitely the limiting factor here because there's no way anybody can really help me with it because it's sitting in my personal branch of, or my personal fork of OMR, and it's not merged. It's now up to about 37,000 lines of code, which I think I was at 28, I think, last time. But there's 4,500 lines of tests in that list, so it's not growing, dramatically fast, quickly. Other than the tests are actually quite good. And there's a cryptic reference to incomplete extensions there. Sorry, I took part of this slide from the last deck, which had a list of all the extensions that I'd created already, and a bunch of them were incomplete. So, so don't worry about that. The primary extensions that I've been using as the core extension, which has some extremely basic things. It's very simple. Func is introducing this basic support for creating functions. Like I separated this out again just because I don't think functions are the only possible compile target that you could use for or use to model with JB2. But it basically has loads and stores of locals and params, and be able to return something and to call other things, and to create, and it includes the actual support to represent a compile unit that is a function. Base contains much of the rest of the original JitBuilder APIs except for the virtual machine stuff, which is in the VM extensions. So base has all of the struct types and field types and pointers and all the arithmetic operations and the ability to load and store fields, and etc. All of that stuff is there. And then the two other new things that are kind of new since I talked last are this JB extension, which isolates all of the JitBuilder calls to a particular extension. So it's only the code inside this JB extensions directory that refers to JitBuilder at all. And OMR Gen, which directly generates to OMR compiler IL, and that has the only references to the OMR compiler at all in that directory as well. And one of the things that I've been doing with that OMR Gen thing is being very pedantic about producing unit tests for everything that I do. So there's as I mentioned, there's like 4,500 lines of tests that test all of the different operations with all of the different combinations of opcodes and various values, including numeric limits of the various types, making sure that the right answer comes back for all of those things when you run them.
Do you manage the tests under JitBuilder 2, or are they under the FB tests?
They're under JitBuilder 2 right now.
Is that where they're going to stay?
I don't know. I haven't thought about that, to be honest. I mean, right now there's a test directory inside each extension, so that has tests that are specific to that extension, because there's kind of like it's using API that's specific to an extension. I don't think it necessarily has to be that way, but again, if we separate things out the way that I talked about on the previous slide, just having, with JB2 not being an OMR compiler, maybe all the testing, it wouldn't necessarily make sense for all the testing to go under the FB tests, or maybe at least not under the compiler test stuff. Maybe FB test is still the right place. I have to think about that some more. That's a good question. That's my last slide. So once again, I'll wrap by just to say I hope you found some of this interesting and the refresher kind of interesting. I do apologize for the confusing nature of the code generator thing. I'll try and come back in a month or something like that and clean it up and do a better job of it. But I'm happy to answer any questions anyone has, or try to.
Is there like sort of an example implementation that you were like? All of this stuff is great, but is there like an example integration of this with something
Anything else? No.
That you want
I mean, other than the unit tests. The unit tests basically show you how you can create functions and compile them and do stuff with them. One of the extensions that I was hoping to create was one for I have a CAS project that has done some code generation work associated with databases.
Right.
So trying to just do some basic stuff to kind of highlight what an IR that's written in JB2 might look like for implementing some of the TCP/H queries, for example. That was one of the things that I was kind of looking at doing, but it requires some data types because you have to be able to represent tuples and tables and attributes of tables and things like that. It's never hit the top of the list for things for me to work on next. There's always been some massive, crazy refactoring that I wanted to do first to make JitBuilder 2 better before I got to the point of having another thing defined and using it. But I mean, the extensions themselves are kind of examples of some kinds of things, and then the unit tests are the other pieces.
Yeah. I wonder if OpenJ9 might be the
maybe
one too.
So the VM, the tests that are in the VM extension are the same tests that we had for JitBuilder, like the test register and test operand stack. So those tests are basically the code samples that I used to have in JitBuilder for register and operand stack. So I mean, it does show some some uses of, or demonstrate some uses of those facilities at least, which are some of the more interesting things from JitBuilder, I would say. But yeah, beyond that, no. All just stuff leaking out of my brain.
Other questions for Mark?
We are still connected to audio, right? Maybe, maybe not.
Okay. Well, if not,
I see a raised hand.
There's a raised hand.
Go ahead, Emery.
How can I know the kinds of code generators for JitBuilder 2?
Basically, there are only two right now, and they're the ones that I mentioned in the talk. So there's code generation. Oh, do you mean like platform code generation, or do you mean like the types of? I mean, okay, let me answer the question you asked, and then we'll see if it's the right answer. There is the JB code generator, which basically translates JB2 into calls to the JitBuilder API from OMR, and uses JitBuilder to generate native code, which can generate code across all of our platforms and operating systems. And the OMR Gen extension, which is the newest thing that I've created, that one generates code directly into, or translates JB2 IR into the OMR compiler IR, and that has been tested on ARM64 and nowhere else at this point. Basically because I'm developing it on my laptop. But in principle, it should work on any platform because it's not generating any, it is doing some ARM-specific stuff in places just because ARM doesn't support all of the, I needed to implement more things on the ARM platform to do widening and narrowing, or mostly widening of small data types for various opcodes, because the code generators didn't support them directly. Like a B to F, I think, for example, is not implemented, I don't think. So I had to do some widening on my own to get B to I so that I could do I to F in the ARM64 code gen. But in principle, it should work across all of our platforms.
It seems like that answers my question, and thank you for your time.
Thanks. Any other questions? I just confused everyone to hell. All right. Okay, I'll come back and try to do better next time.
Okay. Thanks, Mark. All right, well, that was our last topic. So we'll see you guys again in 2 weeks where we have another topic lined up. Okay. Talk to you later.
Thanks. Bye.